Okay. Before I start today's lecture, anyone has any questions? Everything's crystal clear. Any questions about makeup exam today? So this room wasn't available from 3, and I didn't want to have some students here, some at other rooms. So I reserved the room 112, the one next to this one. I guess this side. Anyway, 112 would be the makeup exam 2 at 3 to 6. So you're just welcome to show up at any time in that period, or even at 6 if you cannot make it to the sooner session. How many of you are taking makeup? Oh, you can have your hands up so I know how many I should bring. Okay, 30 roughly, thank you. Okay. Any question about makeup exam 2 or anything specific you want me to talk about before I continue with chapter 9? Everything is good? No questions? Okay. So I just start with what I was doing before. Can anyone tell me what was specific about Bohr model? Yes?
Only works with element I.
Yes. So when we had the emission spectra of different elements, Bohr model could explain the emission spectrum only for hydrogen elements, not the others. What else was specific about Bohr model? It had orbits, exactly. So we had like different orbits around the nucleus. So if this is our nucleus, positive charge, we had certain, is there any question? Just hearing people talking. If you have questions, just feel free to ask me, You know that I don't mind, and I always encourage questions. Okay, so these are orbits around the nucleus. And as you see, I cannot do a good job having a good orbit. That's why I include the pictures from your book. Okay, and then n equal 3. So I give you this in exam. Now I'm kind of like talk police, just seeing who is talking to pick on them. Don't talk, okay? Just ask me questions. And then sometimes, you have a question and you think that is only your question, and lots of your friends have the same question, but they don't want to ask. So just ask me any question, right? I answer them for you, and other students would benefit from that too. So I give you this in exam, and I say, based on Bohr model, which point can be possibly a location of an electron, and I add another orbit around this, and all of these are circles. I apologize for my crooked drawing. But I say, based on Bohr model, which of the following can be the position of an electron? And I name this A, B, C, D, E, F, G, H. So for your exam, you'll be having from 1 to A to D. So no more than that. But based on what I just told you, which one can be a location of an electron? A, right? So what Bohr said is that electrons, unlike what Rutherford said, that these electrons can be just around nucleus. We don't exactly know where they are, they are around. This is what Rutherford came up with. But Bohr said, no, this is not wherever they want. They are in certain orbits. And each of these orbits have certain energy associated with them. So I give you an exam which orbit has the highest energy. And I say n equal 1, n equal 2, n equal 3, n equal 4. And I try the numbers here would be consistent with the option that I give you here. Because even one time when I was I had the solution key myself, the answer was 2, and then I put n equal 2, for instance, in number D, and I automatically answered B because I was thinking of 2, right? So pay attention in exams so you don't make such mistakes, but I try my best, if it's possible, to match these things, so I minimize errors associated with just test taking in a sense. But if I tell you which orbit has the highest energy, which one would that be, or which answer? D. So you can think of it in this way, that when you have a positive charge here, maybe this is not the best choice of color. Okay, better positive charge here, and then you have, and this is our nucleus, and you have electron in n equal 1, positive and negative, they attract each other, right? So it's kind of like this electron cannot freely move because it's under the influence of this positive charge, right? So it doesn't have much kinetic energy, or in general, it doesn't have much energy. That is the lowest amount of energy that this electron can have when it's in n equal 1. But if I tell you I have an electron in n equal 4, you see that this positive charge here does not have much influence on this electron. So this electron can freely move, right? So it has lots of energy. So when we go farther from the nucleus, when the number of n's increase, energy increases. So n equal 1 has lower energy compared to, and this is energy, lower energy compared to n equal 2, that has lower energy compared to n equal 3, and so on. And that is energy 2. So we're comparing energy levels. Does that make sense? Any questions? And as I said, sometimes the students, something doesn't make sense to them in the class, but they don't want to ask specific questions. You can also raise your hand or just ask me to repeat what I said. I try to paraphrase and explain it another way, right? So I make sure that you understand. But ask me questions. Don't let you don't understand something and then go home with thinking of you're going to study or watch the lecture again. Just ask me here. Okay, I'm here to help. So if I ask you which one has lowest energy among this, n equal 1, n equal 2, n equal 3, which one has lowest energy? Exactly. That's why when an electron is excited and goes from n equal 1, for instance, to n equal 3, it's unstable. It wants to lose the energy and goes back to a lower energy orbit. Okay, and then if it goes back, for instance, here, it emits light. So that's why. Okay. If no question, I'm going to ask this. Can anyone tell me what was orbital? So we talked about orbits, and hopefully we have an understanding of what they are. But what is an orbital? Yes?
It's a probability map that shows where the electron might be found.
Exactly. So orbital in general is a probability map. So what quantum mechanical model tells us is that it's not that easy that we have a nucleus and then we have electron around it, at n equal 1, and we say this electron is somewhere here. It's not that easy, okay? So it can be here, it can be here, it can be here, 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 here. And we did all these dots. Remember, we put all of them together and we got a spherical shape geometry, or we got a sphere. And we said we call that S orbital, okay? That was spherical, remember? So in general, just writing or drawing orbitals on paper would be difficult, especially if I have multiple number of electrons. So this is more conceptual, so that's why I asked you to read the book and then follow my lecture. So hopefully you have an understanding of what orbital is, okay? So orbitals are probability of map of where electrons can be found, okay? So as I said, electron can be here, 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 and when we put all those probability maps together, or all the location of electrons at different points or at different times, when we put all of those together, we call that a specific orbital. And in general, we denote an orbital with a letter and a number. So can you tell me, yes, can you tell me if I have p orbital, if I'm like in, p subshell, and we in quantum mechanical model, we had two terminologies. One of them was shell, one of them was subshell. Okay, so if I'm in the p subshell, how many orbitals I can have? Do you remember? So we have more than two, but two is part of that. So basically, if I had s orbitals, right, if I consider like my Cartesian coordinates here, and depending on how you name them, it doesn't matter, x, y, z, it depends on how we agree on having this, okay? And then they can have like, if we have s orbitals, right, we said that the shape was spherical, right? So here, it doesn't matter which direction I have s orbital, right? In each direction that you look at it is a sphere. So that's why you only have one s orbital. Or like if we're on s subshell, we have only one orbital. Does that make sense? Because we don't, if you look at it in x direction, z direction, y direction, all of it is one, okay? But p orbitals, can anyone tell me what was the shape? Dumbbell-like, remember? So if we consider the same, coordinates here, and as I said, these are arbitrary. You can, call this one y, this one x. It depends on how you look at it. So if I have this, one possibility can be this, right? This dumbbell-like orbital would be in the direction of x coordinate. So based on that, can you tell me now how many possibilities would that be? So one would be px that I just wrote, okay? What would be the other possibility?
Dy, dz.
Exactly, the other one would be pz. The other one would be py. That's why when we are in p subshell, we have three orbitals. We call one of them px, the other one py, the other pz. Does that make sense to everyone? And this is the shapes I'm just going to ask s orbitals and p orbitals from you. And also, we have pictures for, if I can manage to make this work, duct count. Okay, we also have d orbitals. You see that now it's more complicated. We have different shapes, and depending on how we arrange them, we have like different types of orbitals. So I only want you to know that we have 5 different p orbitals, but I don't ask you the geometries or anything like that, okay? As long as you know s orbitals are spherical, p orbitals are dumbbell-like, okay? You don't need to know the shape of the orbitals, but I expect you to know that we have, going back to what I was, okay. I expect you to know that when we are, let me write that for you organized here, so you have that. And if you looked at the slides that I posted on Canvas, I also included the pictures of your book, so you have that. So I highly encourage you to study that. But I also included this in the previous slide. So if we are in shell n equal, so I write it like your book wrote, but for me it would be convenient that I start with n equal 1. So this shell is the same as orbits in Bohr model, okay? Shell and orbit, they are the same. So when we're talking about shells, we're talking about orbits, n equal 1, n equal 2, n equal 3, okay? And we call them principal quantum number. This is like fancier way to name them, but that is the same. That's why we said Bohr model is really important, and we should learn that because we use that in quantum mechanical model. And then we have number of subshells. Okay, whatever this n is, the same number you have subshells, meaning that if n equals 1, you have 1 subshell. If n equals 2, you have 2 subshells. If n equals 3, how many subshells? 3. If n equals 4, 4, right? So whatever the number of your shell or principal quantum number, the same number is number of your subshells. So it should be easy to remember. And also, we have letters specifying subshells. Specifying subshells. So if n equals 1, we only have 1 subshell, and that is S. And you should remember, okay? If n equals 2, we have 2 subshells, S and P. Okay? If n equals 3, we have 3 subshells, S, P, D. If n equals 4, we have 4 subshells, S, P, D, F. So I'm going to ask you what is the shape of S orbitals, or like, S subshell, or like P subshell. But the D and F, I'm not going to ask you the shapes. But you should know this semi-table that I wrote here. And if you, or your book called that figure, that is your figure 9.19. Any question about that? So if I ask you in an exam, how many subshells exist in n equals 3? 3. Or I say, which of the following does not exist in n equals 3? S, P, D, F. F, right? So hopefully this is clear, because we're going to use that extensively from now on. So the first step is for you to know this figure well. Any questions? Good? Okay. The next thing that I'm going to talk about is energy. So when we talked about orbits, we said n equal 1 has lower energy compared to n equal 2. N equal 2 has lower energy compared to n equal 3. N equal 3 has lower energy compared to n equal 4, and so on, right? That goes on. So what about orbitals? And remember, when we're dealing with orbitals, we denote each orbital by a letter and a number. So I'm going to write that. We specify each orbital by a letter and a number. For instance, I say 1s, or 2s, or 2p, okay? Or 3s, 3p, 3d. Can I have 3f? No, right? Why not?
It's a higher orbital. It has 4 shells, and it can't have F if it's lower.
Exactly. Remember just the figure that I had before. And as I said, I'm trying not to go back and forth between the slides, because when it's, record me, each slide is associated with what I'm talking about, so I'm trying not to go back and forth. But we said in n equal 1, we have one subshell that is S. N equal 2, we have two subshells that is S and P. N equal 3, we have three subshells S, P, D. N equal 4, we have four subshells S, P, D, F. So if I give you an electron configuration that I'm going to talk about momentarily, and it has 3F in that, that is wrong. Or if I give you 1P, that is wrong. Okay? Does that make sense? And that is why I asked you guys to study after each session, because I know, most of you, if not all of you, learn things in class, but then you go home and then forget about things, come back to the class, and now it doesn't make sense anymore, but you learned that. So you need to just practice to make sure that we are on the same page. Anyway, so this one, that specify my number of n, so this tells me that I'm in n equal 1. So we call that, shell or orbit, right? Orbit was Bohr model, how Bohr named that. Or we call that principal quantum number, right? And the same thing here, 2, 2, 3, 3, 3. So n, the number tells me what shell I am. The letter specify what subshell, and also specifically the shape of the orbital. This S tells me that I have a spherical orbital, okay? Or like P is like dumbbell-like, right? So we specify each orbital by a letter and a number. And I give you this in exam, and I say the number specifies the shape of the orbital. True or false? False. The number specifies the shell. The letter specifies the shape. Any questions? Okay. If we learn this, I'm going to talk about energy levels. And we use that to write the electronic configuration. So I need all of you guys' attention. Just don't think about anything else, your lunch or like your exam or like your other courses. Just be here with me, okay? So if I ask you, which of the following energy levels are correct? And I here write, n equal 1, n equal 2, n equal 3, for instance. Or I write n equal 2, n equal 1, n equal 3. You see that this is like the y-axis here, energy is increasing, right? So this point in the graph, or like here, has higher energy compared to the here. You all know how to read graphs, right? Is that do we have any questions? Good? Okay, let me erase the other one, not to be confusing. So when we have energy like this, here we have like lower energy compared to here, for instance, right? This has higher energy. So energy is increasing from here to there, okay? So if I give you something like this in exam, and I say this is A, this is B, this is C, which one of these makes sense? A, exactly. Okay. So have that, and as I said, this was, basically Bohr model. We just were dealing with orbits, nothing more. But now we have orbitals, so they have a letter and a number. So how we do that for Bohr model, for quantum mechanical model, or when we're having orbitals, is the following. We have like the same energy scale. And now, if I want to compare 1s with 2s, which one of them do you think has higher energy? 1s or 2s? 2s has higher energy, right? As I said, Bohr model is still valid in so many instances, and that's why we use that extensively in quantum mechanical model. So if we have the same orbital, or if we still have like we're working with S soft shell, and the only thing that is different is the number 2s has higher energy than 1s. And now I'm telling you, and this is kind of like you just remember, that 2p has higher energy than 2s. And you can just remember that we said 2s, 2p, so p has higher energy, okay? And as you remember, we had 3 different configurations. One of the dumbbell-like orbital was in the direction of x, the other one was z. I'm just like moving my hand, but you know what I mean, right? One was in the direction of x, the other one y, the other z. That's why in p soft shell we have 3 p orbitals. Does that make sense? Any questions? Yes.
So in terms of like subshell S, how many orbitals would that have?
Just one. And the reason is that as we draw that, when you look at the S soft shell, and if you look at it from x direction or y direction or z direction, they are all symmetrical. It just gives you one configuration. But for P, it's not the case. Great question. Any other questions? Okay. So 1s has lowest energy, then 2s, then 2p. And now we go to another shell, right? So 3s has higher energy than n equals 2. And the same thing here. We have 3p. And each of the p orbitals in p subshell, they have similar energy. So px, py, pz, the energies are the same. That's why I have it like level. And I try to write it as level as I can. But as you see, this, that, or I guess I highlighted this, that, all of them, they have the same amount of energy. Okay? And then 3s, 3p. So far, it's kind of straightforward, I hope. 1s, 2s, 2p, 3s, 3p. Here, you have an exception. So we said that in n equals 3, we have 3 subshells, right? S, P, D. So probably you assume that next I'm going to write 3D, right? Probably you think that now, next I'm going to write 3D. And I'm not going to ask you the shape, but I asked you to remember that in the subshell, we have 5 d orbitals. Remember the configurations that I showed you, that I told you I don't want you to know? But there were 5 of them, okay? And depending on the geometry that they had, there was like 5 of them. We have 5 d orbitals. So you expect that after 3s, 3p, we have 3d, right? Based on what I just told you. Does that make sense? But here we have an exception, and 4s actually has lower energy than 3d. So first, let's just like kind of review this. 1s has lowest energy, okay? And we only have one s orbital, that's it. Because in n equal 1, we had only one subshell, and that was s, right? And then when n equals 2, we have 2 subshells. Maybe do this. And then those were s and p, right? And then when we had, let me change my color. Okay, when n equals 3, we had 3 subshells, and that was s, p, d. And n equals 4, we had 4 subshells. And those were S, P, D, F, right? So when you want to compare the energy of the orbitals, as we said, you should have a letter and a number, right? So can you tell me, whenever you look at me, I'll ask you. Okay, can you tell me, based on 4s, okay, if I ask you 4s, what is the shape of this orbital? Spherical. Does that make sense? So S, when you hear S, automatically it means a sphere. Okay. So what about 4p? Dumbbell-like, right? So in 4p subshell, when I say 4p, just I'm referring to p. How many p orbitals I have? 3, right? So as I said, don't want to study at home or think about your other classes right now and then think about this later. That doesn't work out. Just listen to me now. Try, to understand everything now. Okay, so going back here, we have one S and that's it. We don't have 2S we have 2S, but we don't have 1P, remember. So when you have 1, you only have S, okay? When you're dealing with 2, the number here is 2, you have 2S, 2P, okay? And first you fill out 2S and then 2P, okay? And then what about n equals 3? We have 3S, 3P, 3D, okay? So based on what we talked about, first you fill out 3S or write 3S, then 3P, right? But we hold on to 3D. And the reason is that 3D has higher energy compared to 4S. So this is the exception. Here first we fill out 4S, and when I say fill out, I mean we fill them out with electrons, which momentarily it makes sense. But here in the energy diagram, we write 4S sooner because it has lower energy compared to 3D. And when we're dealing with D, we have 5 different orbitals. And kind of refresh your memory, you see that when we have D, this is the 3D orbitals. The figure shows both the dot representation and shape representation of each D orbital. You see, one shape is like this, the other is like that, the other is like this. This one is like a donut that has a dumbbell in it, kind of. The other is like this, you see. As I said, I'm not going to ask you the shapes, but I expect you to remember that it was 1, 2, 3, 4, 5. Okay, like your, dumbbells here. Here you should know, I asked you the shape, but it's like 1, 2, 3. That's why we have 3 p orbitals, okay? But for S, it's only 1, right? If you look at it from Y direction, Z direction, and X direction, it's all the same, okay? And your book even didn't bother to write it for F orbitals. It would be even more complicated, and it would be 7 different possibilities. Okay. Any question about that? So can anyone tell me, when I have one hydrogen atom, if you consider one hydrogen atom, how many electrons you have? 1, right? And where do you put? So in Bohr model, we had these orbits, and we put electrons in each orbit. Remember, we said that the first orbit had maximum 2 electrons, the second orbit had maximum 8 electrons, and then we kind of had like the Bohr diagram, put the electrons in each orbit. As you may guess, we want to do the same now with orbitals, right? So if I have only 1 electron, where do you think I put that electron? 1s. Why? Why didn't you put that in 3D? I don't know. Because that has lowest energy. So the electron wants to be in lowest energy possible. That's why when we put electrons in Bohr model, we put them in n equal 1 first, because that is the most stable configuration, that is the most stable. You remember ground state? That we said that's the lowest energy that the electron can have. So that's why we start with the lowest energy. And in this energy diagram that I showed here, 1s has the lowest energy. Okay, so based on that, how do you think, if I want you to give me an order of filling electrons, right, or filling orbitals with electrons, what do you think the order would be based on what you have here? We start with the lowest energy possible and increase the energy, right? Yes?
Would it be 1s, 2s, 3s, 3p?
So yes, 1s, 2s. But after 2s, which one has lower energy compared to the rest?
2p?
Exactly. What after?
3s?
Uh-huh.
3p?
Uh-huh.
4s?
Uh-huh.
And then 4d? I mean, sorry, 3d, sorry.
Exactly. As your friend said, you look at this diagram and then write these orbitals, exactly as how she did. And sometimes you know the answer and then just make a mistake. Instead of 3D, write 4D, you know. So just pay attention so you don't lose points when you know the answer. And if you know this order here, you can write the electron configuration for all the elements that I give you in the exam. So for the purpose of our class, if you remember 1s, 2s, 2p, 3s, 3p, 4s, 3d, you can answer the questions, okay? Are we all good with this order? Does that make sense to everyone? Yes?
There's some shorthand to writing it, like, because depending on what element you're writing, that would take forever.
It's for all the elements. We have 2 exceptions in the periodic table while using this rule or like these energy levels that we're not going to talk about in the class, and I'm not going to ask you in the exam. So for the sake of our class, as long as you know this order, electrons always fill the orbitals in this order, okay? Any questions? Great question. Yes?
Does it still take the same number of electrons to fill each level?
That's a great question. That is what I'm going to talk about next. Any other questions? Okay. So if you learn this, now my job would be much easier now. So in each of these orbitals that you see, you can have maximum 2 electrons. And each orbital, when I say each orbital, I mean like this, 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 this. So each of these we refer to, you know, one orbital. As I said here, this is p subshell, and it has 3 orbitals, okay? So in each orbital, we can have maximum, you know, 2 electrons. And how we write the electrons is that you can just show them with 1 arrow or half arrow, okay? You can also write the whole arrow, but your book wants to be concise, so that's why we write that like that. And we also have a property. So this is like several concepts, and then your book tries to condense everything in like 2 pages and explain it in really simple words. So some of the things that they say, you may need more explanation or more reading to kind of understand everything. But your book says that electrons, they have a fundamental property that we call that spin, okay? And electron can be spin up, meaning that this arrow that we have here will be towards above or like up, right? Or it can be spin down. And in each orbital, you cannot have the same spins, okay? In other words, if you consider this as an orbital, you cannot have this, or you cannot have this. You should have 2 spins with opposite directions. One of them up, the other down. And I welcome you to come to my office hours or like email me to explain more about spin. But as of right now, for the purpose of our class, you remember that electrons have a fundamental property. We call that a spin, and the spin can be whether up or down. And in each orbital, you can have maximum 2 electrons with opposing spins. Does that make sense? So imagine we want to fill these orbitals. So the first one I put 1, 2, okay. And you can have the direction reversed too, but as long as they are opposing spins. Okay, so 1 arrow up, 1 down. You can also write it as whole arrows. That doesn't matter. Your book wrote half arrow to be more concise. And sometimes when we have so many of them, it would be more difficult to demonstrate. That's why it does that. Any questions so far? Good? The other rule that we have is the following, that when we have orbitals with the same levels of energy, with same amount of energy, for instance, 2p, right? We have 3 orbitals, one of them px, py, pz, right? Remember that each of them has the same amount of energies, right? How we do field the electrons is the following. First, we field them singly, meaning that first I put them like this. That was an error. Okay. After we put that, we pair them next. Okay. And I'm going to solve some examples so it becomes more clear. But as of right now, remember that when we fill these orbitals, for instance, if you want to put 2 electrons in p subshell, okay, you don't put it like that. Or you don't put it like this. I guess. I don't know. So what you do, first start from the first orbital here and then put the next one here. So we feel when we have orbitals with the same amount of energy, we fill the orbitals singly first and then we pair them up. Does that make sense? Does that? No? Okay. For instance, here, imagine I want to put 5 electrons in 3D, okay? And if you took any, let me erase this so I can demonstrate better what I want to say. Okay. If you took any statistical course at any point, or like, if I tell you that I want to put 1, 2, 3, 4, 5, right? I want to put, and I told you that I have an arrow, I demonstrate an electron with an arrow, right? So if I want to put 5 electrons here, right? There are different possibilities, right? So one possibility is that I do this, 1, 2, 3, 4, 5, right? And I said in each of these orbitals, I can have maximum 2 electrons with opposing spins, right? So I cannot have 3. So if I write something like this, or something like that, that doesn't make sense, okay? Or I cannot have this. I can have maximum 2 electrons with opposing spins. That's why these are wrong, right? But you may tell me I want to put these 5 electrons like this. Okay. Let me write this 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. The other possibility, one other of you might tell me, what about this? 1, 2, 3, 4, 5. I like to feel it like that. One other might say that I do 1, 2, 3, 4, 5. Right? You may feel these with different directions, right? So what we say, which is basically Hahn's rule, and I'm going to write the rules later on and then also include your book so you have the text so you don't have to worry about that. But what Hahn, the scientist, said is that when you want to fill these orbitals, 1, 2, 3, 4, 5, that they have similar amount of energy, you cannot do it however you like, okay? What you should do is that first you put 1 electron in the first one, then another electron in the next one, then another electron in the next one, depending on how many you have. In this example that I told you, I have 5, right? So I put 1, 2, 3, 4, 5. I put them singly first. It means that 1 in each of them. Okay? And then pair them up. So even if I have 7 electrons and I want to put them here, right? So if I have 7 electrons, I first put 1 here, second one, third one, fourth, 5. Now I fill them singly, right? Now I go back and pair them. Okay? So I put the 6th one here, 7th one here. And that I called Hahn's rule, which says when filling orbitals of equal energy, we fill the orbitals with electrons singly first, then pair them up. Okay. So now that we learned that, if, again, 1s we can have, or 3s we can have maximum 2 electrons with opposing spins here. So here, if I just write the answer, you cannot say if I did it right or wrong, because maybe that was wrong, remember. But if I have animation, it would be like 1, 2, 3, first fill them singly, then I pair them up, okay? And then 4s the same. So 4s, basically, we did the same thing too, right? We filled 1s singly first, and then pair that up, but pair that up. But it's only 1s, so automatically it's just like fill them up. So the next one, 1, 2, 3, 4, 5, and then we pair them, okay? So based on what I wrote here, and I hope I could explain that somehow that you understood, what is the maximum number of electrons in 1s orbital? 2, right? What is the maximum number of electrons in 2p orbitals? If I ask for all the 2p orbitals, or like p subshell, would be 6, right? What is the maximum number of electrons in d subshell? 10, right? Does that make sense why that is? Each orbital can have maximum 2 electrons with opposing spins. Okay, so for instance, I have 1 minute. I'm not sure if I can do that. So if I have carbon, maybe I can. So the atomic number of carbon is 6, okay? Now I want you guys to have at least one example. So I write 1s. How many is the maximum number of electrons here? And then I write 2s. What is the maximum number of electrons here? And then I write 2p. What is the maximum number of electrons here?
6.
In 2p. So we have 6 in total. I already put 2 electrons here, and then 2 electrons here, right?
2.
Exactly. So 2 plus 2 plus 2 would be adding up to 6. So we call this electron configuration. When we put electrons in orbitals, and then you see how we fill them out. Any questions? Okay, if no questions, I see you at room Renfrew 111. I'm going to write it here. Renfrew 112. I was thinking of 112. I said 111. It's the next room, okay? No, you're free to go.